Hello, and welcome to Unnatural Numbers, the YouTube maths chat show that puts the fun back into functional analysis and mate back into matrix. I'm here today joined by three fabulous guests. We have got Allison, who is a part-time professor of computer science and full-time founder of a finance company. And also joining her today is Sasha, who is the Dean of STEM, but together they are the co-authors of an infinite series of children's books. Welcome, Allison and Sasha.
Thank you for having us.
Hello, yeah, great to be here.
Also joining us is Tomás, who is doing his PhD in Exeter on the tipping points of when things go horribly, horribly wrong. So I'm sure that's not a portentous guest to have on today's episode. Welcome, Tomás.
Thank you.
Today, we are exploring all of the interesting things that we have about the number 6. And to kick us off today is my fact. So my fact about the number 6 is that it is the first centered pentagonal number. Ooh. Okay, that's not really my fact, but it's a fun way to introduce the number 6 in a slightly weird way. What's a centered pentagonal number? Well, in order to identify this, I think we should start with something that we are perhaps all familiar with, and that is the square numbers. So I'm going to say the square numbers are numbers that can be constructed out of a series of dots that form a square. But of course, that's not the only way that we could arrange dots to form a square. So as well as the square numbers, we might also want to consider the centered square numbers. So the centered square numbers look a bit like this. These are ways of arranging dots in a square such that every consecutive layer has 4 more dots than the layer before. Starting with 1 dot in the center, we would then add 4 dots. Beyond that, we'd have to add 8 dots, and then we'd have to add 12 dots. So it goes up by 4. I think this is a much more sensible way of describing a square number, because every time we go from one number to the next, rather than simply adding, well, what's this? From 4 to 9, we've added on 5, and then from 9 to 16, we've added on 7. There's no logic in that, no sense in that at all. Instead, we've added on 4, and then we've added on 8, and added on 12. It's the multiples of 4. That makes a lot more sense. So centered figurate numbers, that is numbers that make a shape that have a value in the center. Those are a much more sensible way of organizing our shape numbers. And in fact, we've got lots of them. For any polygon, we can create a set of numbers that are centered polygonal numbers. And actually, today, I'm not that interested in the number 6, where the number 6 is, of course, the very first centered pentagonal. I'm interested in the hexagonal centered numbers. So that is this column here. So let's focus a little bit more then on those centered hexagonal numbers. And I'm going to give you the first 4 in a sequence. So we start with number 1. We then have to add 6 dots around the number 1 to get 7 dots total. If we then add 12 dots to the 7, we're going to get 19. And of course, after 19, we're going to have to add 18 dots to get to 37. So every time it's going up by another multiple of 6. Well, that's nice and interesting, isn't it? This is a much better way to record the numbers, I think. But what happens if we start stacking them on top of each other? What happens if I put this 1 dot on top of this to form a sort of pyramid of centered hexagonal numbers? How many circles or how many spheres are going to be in this 3-dimensional stack? Well, to calculate this, I think all we need to do is add the 2 layers together. So each pyramid is going to be constructed by layers. I'm going to ask someone from my classroom, what's going to happen then if we add together those first 2 centered hexagonal numbers? Sasha, what do you get if you add those numbers together?
I believe you get 8.
You get 8. Thank you very much. Tomás, what do you get if you then add on the extra layer? So you have 3 layers of your centered hexagonal numbers.
27.
27. Thank you very much. So Allison, I'm afraid you've drawn the short straw. What happens if you add on now a 4th layer?
So that's going to be 64.
It is 64 indeed. And of course, if we have just that 1 layer on its own, I'll do the hard one for you guys. That starts off with just the number 1. So 10 points to the first person to notice. What pattern have I made if I'm now adding on consecutive centered hexagonal numbers? 1, 8, 27, 64.
Perfect cubes.
These are the perfect cube numbers. So I'm going to write this like this in a way that absolutely butchers the notation. If I have the sum of centered hexagons, That's what a hexagon looks like. Up to the nth row, then the sum of this is going to be n cubed. Now that feels weird, doesn't it? Often when we are adding together sets of numbers, we expect to get a polynomial that is always one order higher than the polynomial that generates the sequence. And here, the polynomial that's generating these hexagons is probably something to do with n squared. And so we would probably expect something to do with n cubed. But to get n cubed on the nose, that just feels a little bit too spooky. So I wonder if I could take a minute to try to prove to you why this is going to happen. And I'm going to prove this in the best way that I know how, badly. What I'd like you to do is start off by assuming that these three are going to form a cube. So we're going to take it for granted that those three will form a cube. My goal then is to try and get this extra hexagon to sit on top of the cube in such a way that the cube has grown by one extra layer in all three directions. And I reckon I can do that simply by drawing on a few additional lines. So first of all, I'm going to draw around the hexagon, like so. I'm going to pick the value in the middle of the hexagon, and I'm going to draw lines up here, and another one down there, and another one across there. And can anyone see what shape I've drawn? You might have to squint a bit, you might have to tilt your head, but this is actually just three rhombi, isn't it? Well, it's not a cube, it's three rhombi, but if you pretend that I'm better at drawing than I actually am, it does look a bit like a cube, yeah. So it's like that isometric drawing that we have, that sort of two-dimensional squashed up, squeezed out version of a three-dimensional cube that we're drawing. And in fact, if I were to stretch and squeeze and arrange all of the 37 circles that are on this layer of the hexagon, I could arrange them in such a way that they would form these three rhombi, which in a three-dimensional projection, so going from two dimensionals in three dimensions, would be that extra layer that just sits on top of the pre-existing cube. And in fact, with centered hexagonal numbers, I can always draw these three rhombi over the top that will always show it gives you those three extra squares of the face of the cube. So there is my fact. If you take the sum of centered hexagonal numbers up to n, the result is n cubed. Oh, hang on, I've got another big purple box here. Oh, well, should we push this just one step further? Why do something in 3 dimensions if we could do something in 4 dimensions? Because what I'd like you to imagine now is I'm not just going to take the stack of these hexagons on top of each other in the way that I've described, because that's not really how you stack spheres, is it? If I was to draw this from an elevation view, that would be putting one sphere here, and then the other spheres would look a bit like this, and the other spheres would look a bit like this. And for some reason, we've always got this central one down the middle. And that's not how you stack spheres. If we wanted to have a nice dense packing of a sphere pyramid, of a hexagonal sphered pyramid, if we wanted to have a cannonball stacking, we'd have to do something a bit more close, a bit more dense. We'd have to rearrange them. And in fact, if I was to do that not just up in a pyramid, but stretch it down in a pyramid, I could have a double pyramid of centered hexagonal and also regular hexagonal numbers. And then I could start adding those up to the sequence. And this starts to get a little bit tricky to describe in words. So I think I'm just going to show you a picture. If I add those up in a sequence, they start to look a bit like this. And now, when I take their sum up to the nth term, it gives you n to the power of 4. Exactly n to the power of 4. What? That's just madness. How does it hit it on the nose precisely? I'll tell you what, the proof for this one in the 4th dimension is actually analogous to the proof that we showed in the 3 dimensions. Much like how we can take that 2-dimensional set of spheres and squint a bit and make it look 3D, we could take a 3-dimensional set of these hexagonal double pyramids and move them around a little bit and map it onto a 4th dimensional hypercube. And I'm going to let you do that at home for homework. So that is my fact. Thank you very much.
I'm bad at thinking in 4 dimensions, so I don't know. I have a question, but this shape with the sort of like bubbly spheres that you've drawn here very much reminds me of if you've watched videos of how they land rovers and things like on Mars, that they put them in this big bubbly thing and it like bounces and absorbs the impact. And if you sort of cut your shape in the middle there to have the 2 pyramid halves, that's kind of what it looks like. So that's my only association with that.
Do you know if they use the hexagon base as well?
I don't know. Now I'm kind of curious what their geometry was, because I was
I
not paying attention. I was paying more attention to the bounciness of it when I watched the like simulation video, because it's quite funny like how much it's actually anticipated to bounce. But now I'm wondering if their geometry was sort of based on this.
It wouldn't surprise me if they do use a hexagonal base, because I'm sure, as we all know, the hexagon is the most efficient way to pack things together. And in this dense packing lattice, this hexagonal shape emerges more naturally, especially if you wanted to have a highest volume to surface area ratio. Because the other shape that you could, of course, get from this is a triangle, but that is then going to have a different efficiency rating. I'm not going to say too much more on that though, because I think Tomás might be about to talk to us about the efficiency of a hexagon later on. But it's a really interesting connection with space. Excellent. Up next, then we have Sasha. Sasha, what is your fact today?
So my fact comes from an area of math called Ramsey theory. So it starts off, you're having a gathering or party, and you want to guarantee that you either have three people that all mutually know each other, or three people that all don't know each other. And the question is, what's the smallest number of people you can have at this gathering to guarantee this? So first I'm going to show that 5 is not enough. So suppose I only had 5 people. So here I'm going to represent my people by dots, by 5 people. And then, all right, so I'm going to use a red line if 2 people know each other, and then I'm going to use a yellow line if they do not. So let's say that these 2 people know each other, and these 2 people know each other. These 2 know each other, these 2 know each other, and these 2 know each other. And then I'm going to say that these 2 do not know each other. And so all the yellow lines means that they do not know each other. So what does it mean that we have 3 people that all mutually know each other? That means that we must have a red triangle, right? Which we do not. And then 3 people that don't know each other would mean that we need a yellow triangle, which we also do not have. So here for 5, if you have 5 people, you are not guaranteed to have 3 that all know each other or all don't know each other. But now I claim that if you have 6 people, you are guaranteed. So I'm going to now draw 6 people there. Okay, and the proof goes like this. So I look at one particular person, make this person a little bigger, and this person either has 3 people that they know or 3 people that they don't know, right? Because there's 5 remaining people. So let's say that there are 3 people that this person knows. Suppose they know this person, and this person. Well, now let's look at these 3 people that they know. If any 2 of them know each other, we end up with a red triangle. So suppose these 2 know each other. Oh, we got a red triangle. So then we got our 3 people that all know each other. And the other case is that none of them know each other. So these 2 don't know each other. And then we get that, well, none of them know each other. So these 2 don't know each other, these 2 don't know each other, and these 2 don't know each other. And we end up with a yellow triangle. So in any case, we just showed that we can either find 3 people that all know each other or 3 people that don't know each other. So of course, I assumed that there were 3 people that this person knew. If I initially assumed that there were 3 that he didn't know, it would kind of work the same way, just by reversing the doesn't know with the no part. So so you might ask, like, what's is 3 special? Like, what if I wanted like 4 people that all know each other, don't know each other? What if or like some other bigger number? So it turns out, so Ramsey's theorem, it says that for any number n, if I want to guarantee that I either have n people that know each other or n people that don't know each other, there's a function f of n, so that if I have that many people, I will always can guarantee either n that know each other or n that don't know each other. In fact, it's even cooler. It takes it even another step further, is that, so here I have 2 possible relationships, right? They either know each other or they don't know each other. But suppose we had 3 possible relationships, like they don't know each other, they're acquaintances, or they're good friends. Ramsey's theorem says that, even for three relationships or even more, any number, fixed number of relationships, you will, if you have enough people, you can always find n that are all mutually of the same type. And so for three, but the interesting question is, what's the smallest number of people that you need to guarantee, right? Like, so for three, we know that it's 6. If we have 6 people, we can get 3 that all know each other or 3 that all don't know each other. For 4, it turns out that it's 18, and the proof is much more complicated. But if you have 18 people, you can guarantee 4 that all know each other or 4 that all don't know each other. Now for 5, we actually don't know.
No.
We don't know the answer, and actually, we have a range. We know that it's at least 43 and at most 46. So
That's a really small range. Why can't we just figure this out?
so actually the 46 as the upper bound was only found last year.
Oh, wow.
gosh.
Up until that point, the range was somewhat bigger.
Was it at a party with 47 people?
Must have been, yes. And so, I mean, even if you think about it, if you have 46 people, right? And how many ways can they like know each other, don't? Well, for any 2 people, right? They either know each other or don't know each other. So it's 2 to the power, however many, 2 to the power of 46 choose 2, whatever that is. So that's a big number. So trying all of those combinations. So you have to be, if you're to find this number, you have to be clever. But there's a fun story from the famous mathematician Paul Erdős. So in his time, the range for 5 was actually bigger. But so he said that if aliens came down to Earth and they said, give us the Ramsey number for 5, or we will attack you, or we will destroy all of you, we should set all of our computers working as hard as they can to try to figure out this number. But if they asked us the same question for 6, we should just come up with a plan to preemptively attack them. So he's basically saying we're nowhere close yet. Like we have no chance of figuring out the Ramsey number for 6.
Is there a range known for 6?
Yes, there is a range. There is a range. So for 6, the range is between 102 and 160.
These are really small numbers.
It's small-ish, but again, if you take
But
2,
as an exponent, like
I mean, again, like if you take 2 to the power 102 choose 2, that's a giant number, right? And so it's kind of like, right, it starts so innocently with the number 6.
No, I don't know. I mean, I wouldn't want to tip myself against far more clever people than me, but I reckon if you get 100 people in a room and just start asking them to randomly form links, yes, it's a lot of options, but surely there's got to be a lot of options that are counterexamples. So you're bound to stumble across a counterexample soon enough.
I mean, that depends on if the counterexamples are kind of dense in the random space, right? Which they may not be as you get close to narrowing in the range.
Yeah, maybe. Maybe they've already thought of that. Yeah.
Well, exercise to the viewer to go read the paper for the 46.
For 46,
and
yes. Well, I mean,
narrow it down to 45.
It's on the art. Yeah.
Sorry.
But again, the paper probably, I'm not sure it has like all the code in it. So you have to write the code yourself based on the description. And
an exercise for all of us as well.
What? Yeah, that's going to keep me up at night. One thing I really like about this fact is you've got two hidden versions of the number 6 fact in this one.
Yes.
So that the type of fact of 6 is the first number that doesn't have a property, but also 6 is the first number which nobody knows the answer
Well,
to.
actually,
Is a great one.
5 nobody knows either, but 6 is like the one where like we have no. Yeah, because 5 is between 43 and 46.
Oh,
right?
yeah. I mean, by that
We
point,
still
you
don't
basically
know
know
it, but at least there's a chance that we'll get it. Like sometime, if we use all of our supercomputers, we might be able to get it. at some point. Whereas 6 is the one where Paul Erdős said, like, no, we have no chance, like, you know, in the next.
Coming up for fact number 3, then we have Allison. Allison, what's your fact today?
So my fact today is that 6 is a triangular number, which is a piece of math that I actually run into most in the context of athletics. So for all of our copious number of jocks in the audience for this show that I anticipate, there are these things called ladder drills where you go to the gym and your coach makes you do 1 of something and then 2 of something and then 3 of something and then 4 of something. And I think the reason coaches do this is because you as the athlete totally lose track of how many times you're doing this push-up or this sit-up or whatever it is. And so it's a tool to make you do more. But if you actually know the formula, it's very quick to compute sort of how much these sums accumulate to. And it's not obvious sort of looking at this. So if we think about this sort of sequence of numbers and we're sort of starting with 1 and then we add on 2, then we get a total of 3. And if we add on 3, then we get a total of 6, which is why 6 is in this sequence of numbers. And if we add on 4, then we get a total of 10. And these sums actually follow a very nice formula. So similar to the hexagonal formulas that we were looking at in the beginning, which is that the sum of numbers I from 1 to n of I, so this is the 1 plus 2 plus 3 plus 4, etc., is equal to n times n plus 1 divided by 2. And my favorite proof of this fact is where the name triangular numbers comes from, because you can prove this geometrically by drawing triangles. So if we think about a configuration of dots that starts with 1 dot, and then we have 2 dots, and then we have 3 dots, then this is going to form a triangle. And in general, the formula for the volume of a triangle is not obvious and sort of difficult to understand. But we also can just sort of double this triangle and superimpose it on itself. So if we put 1 dot, and then we put 2 dots, and then we put 3 dots, then we have 2 copies of this triangle, which are now fused together into a rectangle, which has an easy volume that we can count, or in this case, count the number of dots. And so the total dots here is just going to be equal to our sort of product of the widths of these sides here. So we get the 4 times 3, which is 12. But we've double counted since by doubling the shape. So the total red dots, which is what we started with, is just going to be 12 divided by 2, which in this case is 6, which is where this number n, so this is the n in the formula, which is our base layer, our n plus 1 comes from adding on this sort of base layer of the duplicated shape. And then that gives us our product. And then our double counting accounts for this 2 in the denominator. And so knowing this formula is a nice little trick, because if someone asks you to do, let's say, you know, a version of this that you often see in exercises that you do 10 plus 20 plus 30, let's say all the way up to plus 100, then this is the same as just saying 10 times the sum of 1 plus 2 plus 3 all the way up to 10. And there's a quick little formula for this, which is you still have that scalar 10 in the front, and then you're multiplying by 10, and you're multiplying by 11, and you're dividing by 2. And so you can just easily calculate how many this is, which is going to be, so this is going to give you 5. So you're going to get 50 times 11, which is going to be 550, which is a lot of reps to do of push-ups or pull-ups or those kind of things. But this is my favorite fact about 6, that you can prove this triangular number formula geometrically.
So I've got a question for you then. We were talking about figure numbers earlier, and I think we all know the one with the square numbers, and we can write the calculation of this as whatever figure number we're on, so in this case 2 raised to the power of 2, which is where we get the phrase squared. So this is like n squared for a square number. Is there a similar notation that you've got for describing the nth triangular number? Like, could we say n triangulate?
Ooh, good question. I have not thought about it that way. And I mean, there is a succinct notation for this formula, of course, because we can also recognize this as the formula for n+1 choose 2. So in that sense, it sort of doesn't need its own new concept because it also exists. So I often also introduce this fact by doing multiple proofs of it. So you have this geometric proof is probably the cleanest and the sort of easiest to remember, but there's also a combinatorial proof, which uses this sort of this relation to n choose 2, which comes from a kind of natural place, because if you think in this case, n being 3, so if we think about all the ways that we could take 3 dots and choose 2 of them, well, if we sort of don't use the first dot, then we get one way. And then if we sort of think about, okay, if we do use the first dot, then there's 2 ways. And then, so we get this kind of n choose 2 coming out of the fact that we can consider all the combinations that sort of start from a fixed point, and then how many things do we have left? And so you already have this kind of concise expression for this quantity, which, and to me, as a person who thinks combinatorially, is even more natural than the sort of geometric interpretation of the triangles. But I think for that reason, it's like maybe the combinatorists will fight you if you try to come up with a different notation for this.
I mean, I think sometimes, like I sometimes already, like I've seen it as like capital T sub n, but like that's not quite the same. I mean, it would kind of be cool, like if we had like n inside of a triangle meant or something like that.
I mean, when I'm working with my students, I give them this and let them play with it.
I guess I use deltas a lot for quantities of change, especially in time series for financial data. We think as delta as like how much a price is changing. And so for me, that's already overloaded. Like delta is sacred. You cannot, it's not a triangle, it's a delta.
So coming up for fact number 4 today, we have Tomás. Tomás, what's your fact today?
I'm going to look at how 6 appears in stories and how hexagons especially are used in the natural world and in storytelling. So first, I'm going to talk about a story from where I'm from. I'm from Ireland. And if we look at this left picture here, we have this very cool formation of rocks. If you actually go there in person, you can see it is true. They are very cool. But you've got these columns that look like perfect hexagons of basalt out there by the sea. And the explanation, of course, is that these columns were built by giants, So essentially what happened was there was a big giant over in Scotland, really tall, but Ireland also had its own giant, Fionn Mac Cool. And so Fionn was a king who was very wise and incredibly strong. And this Scottish giant is constantly taunting him. I mean, Fionn got so annoyed one day, he took a big lump of land out where now there's Lough Neagh, and he threw it at the Scottish giant, but he missed him and it landed. And that's where the Isle of Man is today. So that's how that was formed, if you didn't know. But eventually Fionn said, fine, I'm going to fight you. I'm going to build a bridge across the water and I'm going to fight you. So he starts building the bridge, and you can see the start of the bridge building here. But the Scottish giant was so big that he actually just wades across through the sea. And Fionn sees him coming and he's like, oh no, I've bitten off more than I can chew here. He can see him coming from a long way off and he knows that he'll never win. So he runs home and he tells his wife and he starts panicking. And despite all his wisdom, he doesn't know what to do. And his wife said, don't worry, I'll sort you out. So she dresses him up as a baby, hides him, and then puts a pile of rocks outside the house. And the Scottish giant comes and he goes, where's Fionn? And his wife goes, oh, he's gone for a while, but normally he breaks these rocks to make milk for my baby. And the Scottish giant sees the baby, which is Fionn, and tries breaking the rocks, but he can't. And he says, well, if this man's baby is this big and he's so good at breaking the rocks, then I could never defeat him when he goes back to Scotland. So anyway, that's a nice story, but obviously not how the rocks were actually formed. But I think still we can use maths to tell the stories and to tell stories like that. So how were they formed, and why do we see them everywhere in nature? Because it's not just the rocks. We see them in flies' eyes. We see them in the skin of lizards. We see them in snowflakes, and with bees on turtles' backs, loads of places. So let's see why. So here's the Giant's Causeway again. So the problem that we have is that millions of years ago, you had a volcano erupting or magma coming out. And the magma was cooling down, but the top was cooling at one rate, and the bottom obviously was like much hotter. So it's trying to push all that heat out through this really thick, viscous magma. So initially, maybe you have some cracks there. There are kind of squarish cracks, like around A there. And they're pushing the heat out, but the magma is moving and it's being pulled in different directions, and it's not very good at it. But if you want to have as few cracks as possible, because pushing this really thick liquid apart is really hard, but also you want to release as much energy as possible. You want as much like surface area coming out. Then, as Ben alluded to earlier, hexagons are the most efficient shape. So the hexagons form because you're trying to release as much energy as possible from the heat underneath while minimizing this shear stress, minimizing the fractures. So, and we can see here there's like three different kind of tessellations you could have, three different ways everything could go out. But if you look at the triangles, you see the way the straight lines are going all the way down. It creates things kind of tend to move past each other a bit more. There's less. It's kind of easier to push things, and the same with squares. So this hexagon shape tends to be more stable as well. Once things have been pushed into that shape, they tend to stay there a lot easier. So moving onwards, we have the bees and the fly's eyes. And the thing with these is that it's for the same reason that the basalt formed, that these are this way. You're trying to maximize one thing and minimize another thing. So with the bees, they want to hold as much honey as they can. But like they don't want to be making too much wax. They're trying to make as little wax as possible. So they're minimizing the amount of wax they have, and they're maximizing the amount of honey each cell can hold. And so you get this hexagon shape. You get a similar thing with a fly. I mean, flies can see incredible things like polarized light and such that we can't see. And their eyes have evolved over millions of years. And basically, they want as many seeing cells as possible, but as little material and gaps between those cells. So again, you get the hexagon because you're maximizing one thing and minimizing another. But that's not the only reason that things have hexagons, because you also have hexagons in snowflakes. And in snowflakes, without getting too much into the dipolarity and all these sorts of things, essentially water at really small scales is a little bit attracted to itself. So we have that the hydrogen is a little bit attracted to the kind of negative oxygen here, and the negative oxygen a little attracted to the hydrogen. But these hydrogens on the outside want to push away from each other. So you have, this is attracted to here, but wants to push away from this one. And then another one lumps on and does the same. And then they start to form these hexagons so that they can kind of push away on the outside, but also like push toward the hydrogen and oxygen kind of together. And this structure on the smaller scales kind of helps things build up more and more until you get these kind of beautiful fractal snowflake shapes. In this diagram here as well, you can see that there's different sort of hexagonal things going on depending on what temperature and pressure there are around the ice. but that's the basic way it works in water. So another reason for hexagons in nature. And then the last one I'm going to look at is hexagons as kind of squish circles, if you like. So if we look at the back of this turtle shell, you can see the hexagons in the middle and then hexagons that stretch out to the sides of the shell down here. Now, if you look here, we've got kind of 4 circles, and imagine I've drawn them, I've put them together well, and they're all touching, so they're kind of like they're in a tessellation. And if we squash those circles together and keep on squashing them more and more, if you kind of look at the lines of how they're intersecting here, you've got this kind of 120-degree angle, and this aim like along here. So you can see how that kind of moves into being a hexagon grid once you've squashed the circles together. So basically here you've got evenly spaced spots where the keratin of the turtle shell is growing from, and those squishing together creates these hexagonal shapes. And there is an element of that with the Giant's Causeway as well, where a truly like homogeneous cooling lava would be imperfect hexagons. And then I've got a football here as well, to just kind of say as a little precursor to what's coming next, actually, that this is true when you're on a flat plane. So when you move up into a higher dimension, if you want to put hexagons into a ball, you need pentagons to finish it. So unfortunately, we can't really generalize in that way to the higher dimensions. Okay. So the question is, if we have these hexagons that tile the plane in 2 dimensions, and they're the most efficient way, what's the most efficient way in 3 dimensions? Well, the hexagon conjecture, the honeycomb conjecture it was called, that it was the most efficient way, was something that goes back at least as far as 35 BC with a mathematician named Varro. So it was a really long-standing thing. And it wasn't proved until the 90s by a man named Thomas Hales. So this is an incredibly long-standing thing that was really hard to solve. And so you can imagine moving up 1 dimension that this is obviously even harder. There was a conjecture from the 1800s called the Kelvin conjecture. And Kelvin never called it a conjecture, but people started calling it that after he proposed a shape that would kind of minimize surface area and maximize volume in 3 dimensions, but that would still tile like a 3-dimensional volume. And it stood for a long time, but again, this was beaten. Some researchers in Trinity College in Dublin actually came up with a shape which I think was about 1% more efficient than the one Kelvin had come up with. And apparently that was what inspired this building here in Beijing that was used in the 2008 Olympics. So we can see that sort of tiling inspired by that there. Okay. So yeah, just to finish up, hexagons are really cool. They appear everywhere in nature, and their mystery is something that's stayed for a long time. I mean, at least as early as 35 BC. But even in those texts, there's references to earlier texts. These are things that have inspired and sparked wonder in so many people. And especially in the Islamic Golden Age, you could see hexagons being used in art, like on this ceiling here or in this mosaic, where incredible patterns were created from these symmetries. So yeah, that's all.
I have just a clarifying question. So when you're saying that hexagons are the most efficient way to tile the space, what is the metric of efficiency exactly?
Yeah, so basically you want to kind of minimize the perimeter of each shape, but like kind of maximize their area.
And presumably you want to fill, and you need something that fills all the space in
Yeah,
and of itself. So
exactly. So
So
yeah,
are you trying to,
sorry.
maximize or minimize the ratio of the area to the perimeter, or?
If you took each shape of your tiling to have like one unit area or whatever, you want to minimize the perimeter of that. And so the hexagon is the shape that minimizes that perimeter.
while being something that tiles to fill the space.
Yeah,
While
and
being something
taking a
that
fixed
ties the
area, given a fixed area. Okay.
Yeah.
Okay, that makes
Yeah,
sense.
It's interesting then that you chose the coastline of Ireland to talk about a minimizing, maximizing ratio of perimeter to area, because famously Ireland has a very fixed area, but its coastline is infinite.
Yes, yes. Ireland and every other country.
Yeah, good.
Not Switzerland. And those are all of our facts for today, which means we move on to our final segment of the show, and that is looking at the OEIS, the Online Encyclopedia of Integer Sequences, my favorite browsing for an evening. Today, I've brought to you A139250, which I'm sure is famous enough that I don't really need to introduce it, but I'll give it a go anyway. This is known as a toothpick sequence. So here, it is measuring the number of toothpicks needed to construct a shape that follows a particular set of rules. And here are the rules. We are going to start with 0 toothpicks. That doesn't require any toothpicks at all. But then at stage 1, we're going to place 1 toothpick in the vertical direction anywhere we like on the plane. So I'm going to have the first turn by placing 1 vertical toothpick, and that takes 1 toothpick. After that, each of our guests today are going to add more toothpicks to the shape. And the rule is that every available endpoint of the current shape needs to be filled with toothpicks such that each new toothpick is perpendicular to the one that you're drawing it next to, and that the middle of the new toothpick sits at the ends of the last toothpick. No toothpicks may ever cross each other either. So, Alison, I'm going to ask you first. How many toothpicks do you think are needed in step 3 of our sequence? So first of all, when 0 on my turn, it was 1 toothpick. How many toothpicks do you think are needed for the third phase? And can you draw them onto the shape plans?
All right, let me make sure I understand these rules. So each new system. Okay, so this would be a toothpick I can add, right? Where the midpoint is there. And then I can also add one like this.
Excellent. So how many toothpicks have you got in your sequence?
So that would be 3.
So there are 3. That's your turn done. So Sasha, it's your turn next. So if you pick a new color and then see how many toothpicks can you add to this current sequence, noticing that you're only adding them to the currently red toothpicks.
Okay, I'll take green. And let's see, I think I can add 1 here, 1 here, 1 here, and 1 here.
Yeah, fantastic. So how many toothpicks are there in the sequence total? Or sorry, in the
So I
packing
added
total?
4, there were 3, so I think there's 7 total.
There's going to be 7 in total now. Yes, this feels like a fairly familiar pattern that we've got going. It almost looks like it's going to be growing exponentially, doesn't it? We've gone for 1, then we've gone for 2, then we've gone for 4. One thing I forgot to mention is that all of these toothpicks are indeed the same size. So you might notice that there's no real gap here or here. We can't add any new toothpicks on those spots, which is then going to be an interesting round for Tomás. How many new toothpicks can you add to the green ones?
So if there's no gaps there, then I can add 4 more, I suppose. We just got our 4 free spots.
Oh, okay. Well, so it's not growing exponentially then, or at least perhaps not in the way that we were expecting it to. So you got 2 at the top, and yeah, there's no gap there, and 2 at the bottom. So how many would you expect that I can add now. So if we've added on another 4, that brings us up to 11. If it's my turn again, oh, hang on, I can only add 1, 2, 3, 4. It's just growing by 4 each time. So the next one is, let's try that again. It's growing by 4 each time. So the next one is 15. Allison, back to your turn.
So I feel like now it's going to be more again, because now we've made it, the shape is getting taller. So now there is a gap, right, between these blue toothpicks.
Yeah. Okay.
So now I'm going to be able to, let's see, so I'll do red again. So I can do 1 here, 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 here. So now we're going to get to 8.
Oh, okay. And I think at this point I might end the drawing game, because I think we've all figured out how this works, and we can check our answers. And yeah, indeed, we had 15, and if you add 8 to 15, the next one was 23, then 35, then 43. Now, these numbers that I got at the top are the first 20, 30 odd terms of the sequence. Can you see how the sequence grows from looking at those numbers? So it's fairly opaque, I would say. So luckily for us, the OEIS have this on their website, which is a toothpick generating pattern. And based on this sequence, I can show you how this pattern grows visually. And yeah, you can see we were following the correct rules, and that was as far as we had got. But I'm going to get a very sore finger if I just keep pressing this button again and again. So would anyone like to guess how they think this is developing and growing? As we watch this grow, and in fact, I'm just going to hit run here, and you can watch it play out. Who's going to be the first person to tell me what pattern they are noticing?
Looks like fractals.
Yeah, it's our favorite F word. It's a fractal. So this is a toothpick fractal generated from a really simple pattern that anyone can do at home. Just where can you add on more toothpicks to a pattern? And it grows in this oh so pleasing space-filling way of a self-repeating pattern of a fractal. And that's our OEIS for today.
It is very cool. I've never seen it before.
There are actually quite a few different versions of this we can do as well. So there's a few others that we could have a look at. Oh, hang on, reset that. So should we try just another one at random? Should we do the hexagon
Are
one?
these different versions driven by different rules, or how you start?
I'm going to say yes, but that's all you're going to get from me, because I haven't looked at any of the others. But I'm going to guess it's the hex. Let's see if we can work out what the rule is. What can you see happening? It's like a hexagon version of it.
Yeah, it was just
Adding
like
on toothpick.
hexagonal fractal.
Oh, I see. So it's just like the units are not lines anymore. The units are now hexagons.
Yeah, I guess. And it looks to me as though you're not allowed to place one so that it's in contact with a pre-existing hexagon. That's what I'm saying. So once you're about to touch another hexagon, you have to stop. So you hit run, and you know it's obviously it's going to be a fractal, because they're all going to be fractals here. That's quite pleasing. Go on, should we do one more random one? Who wants to pick one? I love it when they just say it's a variant. That's always fun.
What's H neighbor squares? Let me have a look at that one.
H neighbor squares. Sorry, 8 neighbor squares.
Oh.
First person to spot the pattern. What's happening? Oh.
So it looks like you're not allowed to touch a side, but you're allowed to touch a corner.
Yeah. So why?
Yeah, they're adding little squares.
So I think it has to come from the corner as well. So that here we can't have any more on the sides. If we put one here, for instance, that would have overlapped. So it has to come from a corner, and
That
it can't.
seems like a kind of awkward rule.
Yeah. This reminds me a lot of the Game of Life. Are you guys getting that vibe?
Yeah. Well,
yeah. But I'll tell you what, if you scan that code, you'll come through to our website. So that's going to be fun. Nice. Well, that was really good. I liked that. And so that brings us to the wrapping up of our chat show. And this is where we get to talk to our guests about what they'd like to share with you, the audience. So let's go over to Sasha. Sasha, what have you been working on recently?
Yeah, so Allison and I have recently finished writing our second fiction book. So it's a series of books that introduce children to mathematical concept through stories. And our first one introduced the concept of functions through magical beings with powers. And our second book So our first book was called Funville Adventures. Our second book, which is called Module Town, is teaching kids about modular arithmetic through characters that have many hands and different sleep cycles. So the modularity is kind of intrinsic to the character, like each character has an intrinsic modularity to it. This is the cover that I'm sharing of the new book, and the new book we are gonna have a campaign, Kickstarter campaign for it starting next week. So it's not yet published, but it's finished and it's in the process.
So when can people go out and buy this book then?
Yeah, so the campaign is gonna start next week, and it's gonna be running for about a month. But then, so that's the first time you can kind of order the book, pre-order it, and then anytime afterwards as well.
So pre-orders on the link that is in the show notes, and that will take you through to Kickstarter. And then if that is successful, when that is successful, go out and buy it from the website, which is also linked in the show notes as well.
Yeah, and it'll be available on Amazon as well.
Lovely stuff. Is there anywhere that you'd like people to go to find out more about you, your work, and what you're doing?
I think not. Well, the Natural Math website has also a lot about like our first book, and it's going to have also a page for the second one as well. So that's the best place to learn about the books.
Fantastic. And Allison, if people wanted to hear more from you, where would they go?
Sure. So I have a website, thecomputersciencecomedian.com, where I put all of my sort of projects and work. We also have a company blog that you can find at prooftrading.com, which is a great resource if you're interested in learning about the mathematics behind finance, because one thing that's very unusual about us as a company is we do public-facing research instead of keeping our algorithms proprietary. So that's often a good resource for people interested, in particular in the niche of finance of US stock trading for institutions.
Excellent. And again, links to that in the show notes. And Tomás, if people want to hear more from you, where could they find you?
Go read their book. Sounds great. I have an Instagram, Tomás Buckley. I probably might set up a YouTube channel or something soon, but nothing set up yet. So yeah, if I do create something, follow me there and I'll link you to it.
And of course, watch this space on the Exeter Maths Department website for a publication from you in 2 to 4 years.
Yeah. Maybe you might have a small paper in a year's time on return tipping.
Lovely stuff. Well, thank you very much, everyone, for joining me today. That's all that we have time for today. Next time, we'll do the number 7 with a new set of guests. You guys take care now. Bye-bye.
All right, bye.
Bye.
Thank you.